Sum is to add. What's product? Multiply. Whose product is 143. So we're saying that the first one times the next one. First one times the second odd integer, when we multiply them, is 143. That make sense? So this is the quadratic we got to solve. We're going to distribute, and at the same time bring the 143 over. Is that okay? Yeah. Now you can attempt to factor that if you want. Factors of 143 that subtract to be 2 is what we're looking for, because this is a 1 right here. That's hard to know. Most people don't know there are 143 facts. We could try some things out. We could try and see what goes into it and see if it works out. Do you want to do that, or do you want to graph it, or what do you want to do? Because we got to get this thing solved somehow.
Let's just guess some numbers.
You guessed some numbers? Okay. So let's take 143. 143, and let's just see if we can prime factor it, because if we can, we can get it clear to the bottom, then we can see some different combinations of numbers that multiply to be this. Is that okay? Okay, so 2 won't go into it, 5 won't go into it, 3 won't go into it, because this adds up to 8, which 3 won't go into. So I've tried 2, 3, and 5. We should try 7 next. Does 7 go into this? You have to use your calculator to figure that out. No. And by the way, I'm only trying prime numbers for a little while. I mean, 143 divided by 7. Nope, that's not even. What's the next prime number after 7? Not 9. 11. So 143 divided by 11. Oh, that worked. So this number right here, based on what we just divided and what we got, is 11 times 13. And thank goodness their difference is 2. Because these are both prime numbers, and it's not going to factor any further. But because 13 minus 11 is 2, those are going to be our 2 factors. You see what I'm saying? So if I factor this, I'm going to have an x here and an x here, and an 11 here and a 13 here. But to get a positive 2 out of it, the 13 will have to be positive and the 11 negative. You understand all this? Yeah. Equals 0. So that means that in this case, x could either be 11 or negative 13. Which one is it? They both are. Now I need you to understand that 11, listen carefully, 11 and negative 13 are not consecutive odd integers. You need to clearly understand what you have found here. You have found candidates for the first of 2 odd numbers. If x is actually 11, then the 2 consecutive numbers we're talking about are 11 and 13. But if the x, the first of the 2, is negative 13, then the next one is negative 11. And sure enough, 11 times 13 is 143. Sure enough, negative 13 times negative 11 is 143. Which set is it? Both of them. Both of those serve as 2. There's 2 different sets of consecutive odd integers that do this. And they're right there. Because you got to understand that when you found x and both of them were odd numbers, those are both these guys right here. You got to find the next one by adding 2. Because this only solves for the first one. And there are 2 possibilities. Do you understand? You see what I'm saying? Okay. Other questions? Yeah.
Could you help with 57?
With what?
57.
57. Restaurant sells 330 sandwiches each day. For each 25-cent decrease, now we're going to cut the price down instead of build it up like we did with that magazine. We're going to cut the price down a quarter at a time. The restaurant sells 15 more. There's 15 more people willing to buy a sandwich every time they reduce it by a quarter. How much should the restaurant charge to maximize daily revenue, and what is it? So as you remember, revenue is found by taking the number sold times the price you're asking for each one. And to write these, we have to start out with what we have right now. We have 330 people. And to that, we're going to add 15x, where x is the number of quarter decreases in the price. 15 times that, right? However many times we come down a quarter, 15 times that is how we're going to increase our people that are going to buy one, okay? The price that we're asking is $6 right now, but we are going to subtract 25 cents this many times. Does that make good sense? So we graph that. And we have have to be sensible about the window. So I'm going to go to y equals. I'm going to type that in just like it says. 330 minus 15x, close it, 6 minus a quarter. Okay, for a window, how many times do you suppose you can reduce the price a quarter without losing profit? How many?
Probably only like 1 or 2 times.
Yeah, probably. Feasibly, it's going to be, I mean, can we try, what? Give me a guess. 5. Let's try that. So we're going to go, the x minimum is going to be 0, and the x max is going to be 5. That's the number of times we're going to change price. But how much are we making right now? That's revenue. That's what the y is. So 330 times 6 is what?
$1,980.
1,980.
Yeah.
Okay, so we're making close to $2,000 right now before we even decrease the price. We're hoping it'll go up, right? And so we should probably start the minimum at. Here's my thinking. I'm gonna start the minimum at around 1,500. I know that's way below what we're making now, but I want to be able to see what's going on up here in the top part of my screen and not interfere with the writing down here. So I'm gonna let the minimum be quite low so that the graph will be up higher.
Okay.
So I'm gonna go 1,500. Right now we're making about 2,000, so I'm gonna go 2,500. Perhaps it'll be somewhere in there. Okay? And that's a difference of 1,000, so I'm gonna count by hundreds. Okay, let's graph that. Hit graph and see if we can see anything. I think I typed it in wrong. 330 minus 15x, 6 minus 0.25x. Oh, I had minus, should be plus. Wow, you can hardly see any difference at all in it, right?
Yeah.
So here's how we're gonna have to test it to see if we got a maximum. I'm going to go second count a maximum. And I'm gonna go clear over to the left edge of the screen where we're not gonna change the price at all. Now, it appears as you're going along, it looks like you're just tracing a nice horizontal line, right? If you look very carefully, the y values are changing, but not by much, not so much so we can even change a pixel. So I'm going to clear over to the other side, and I'm going to say, that's my length boundary. I don't see a clear maximum. So I'm going to hit enter there, and then I'm going to give it a right bound, I'm going to scoot over there. I'm watching my y values. I'm not watching my cursor move across the screen. I'm watching my y values to see if they go up. They are going up. When they start coming down, I'll know I have a right bound. Does that make sense? Yes or no?
Yes.
Yeah? Okay, so I'm going to keep watching mine. I'm going to keep going. Oh, mine's starting to come back down again where I'm at anyway. So I'm going to hit enter, and then enter. And it does find a maximum on that thing that appears to be horizontal. It's just such a very subtle difference around it that I have to watch the numbers to see it. And so it appears that if we change the price once to, what would it be? If we change the price once, what would be the price of a sandwich?
Oh, it would be 5.75.
Yeah, we're going to reduce by a quarter one time, because that's what the X says right here. One change, one reduction of a quarter makes the price of the sandwich now $5.75. And if we do that, we'll be making $1,984 or $83.75. What were we making before? $1,980. I would not make. What's that? I would not make this change for the extra $3.75. And I'll tell you why. Because it's a lot easier to make change quicker and have my business run smoother and make people happier. It's a lot easier to make change on $6 than $5.75. I would not make this change. For the extra $3.75 is not worth it. But if you're doing the math problem, which we just did, this would be the answer. Okay. Other questions?
Should you also do 67?
We can talk about it. There's one thing I really hate about this. They've made all of those planets in the picture look like they are the same size. That's ridiculous. And it's deceiving. And I know that you know that they aren't the same size, but it can still be deceiving when you look at them all. What you have to look at is the gravity value. Gravity on Earth is 32 feet per second every second. That's the acceleration due to gravity. On Mars, it's only 12. People aren't aware of this. I mean, Mars is supposed to be closely related to Earth. It's about the same distance from the sun, a little bit farther out, and so it's got almost no atmosphere, and it's got way less mass than the Earth. So it's only 12. Jupiter, though, is 76. So it says, when an object is dropped on any planet, the height in feet after t seconds can be modeled by negative g over 2 t squared plus h naught, where h is the object's initial height and g is the planet's acceleration due to gravity. Suppose a rock dropped from the same initial height on the 3 planets shown. Make a conjecture about which rock will hit the ground first. Justify your answer. It will definitely hit first if it's dropped from the same height on Jupiter because it falls a lot faster. It's being pulled a lot harder because the G component is much, much bigger. Okay. Any other questions? By the way, if you were trying to walk, Jupiter's a gaseous planet, but if it were solid with the same gravity that it has now, you would not be able, with the bodies that you have, be able to walk on there. It would crush your legs if you tried. Anything else? Nice thought. Okay. All right, then get those submitted on Big Ideas if you're eligible for that. Otherwise, you can turn it in on paper. If you have that done, you may turn it in right now. If you don't, hang on to it till it is done. Ready? So section 3.2, and I got to record it because we got some people that are quarantined. So before we actually go to the lecture on this, I want you to look at page 103, and I need your eyeballs on that graph, that chart. Goodness.
I accidentally started when I clicked back over there.
I see. Okay, well, we're 12 minutes into this. Here goes section 3.2.
Sorry.
Okay. Well, maybe they'll get help with the point with convoluted disorder. Okay. We're on page 103. And there is a chart on there. It looks more like a flow chart than anything else. It's at the top of the page in those kind of tan colored boxes. Are you looking at it with me? And I want you, instead of reading it from the top down, I want you to read it from the bottom up. So we're going to start with that bottom one, which is called the natural numbers. The natural numbers are those numbers that you use to count with. They were the first ones you learned when your parents were so excited to call your grandparents and have you count to 10 to them over the phone. Those are natural numbers, and it's an infinite set. There is no highest natural number. Starts with 1, and it's what you use to count with. And every day when we take attendance in here, we use the natural numbers to find out who's missing. Okay? And it does not include any fractions or any negatives. The next biggest set, even though the natural numbers is an infinite set, every single set as we move up is going to get bigger and bigger and bigger, a bigger infinity, if you will. Don't let that bother you. The whole numbers are exactly like the natural numbers, except you include the number 0. And the reason why that's in the whole number set is because nobody starts counting something with 0. I don't start counting over here with 0 because Cassidy counts as 1. But we need the number 0 for things like writing the number 40. We need a 0 there. We need something to hold a place if there's nothing there. And, well, I won't go any farther than that. But the whole numbers is different from the natural numbers, but only by one element. Then you move up another one, and you take all the whole numbers and add a few more to it, and you get the set of integers. What did we add? All the negative whole numbers. So there's no start point for the integers, but there's also no fractions. It goes on either side of the number line, but it only includes those whole spots. There's nothing in between included in the integers. So while -5 is an integer, -2.5 is not. You okay with that? So to finish filling in the number line with all those gaps in it, we go to the next set of numbers. They're called the rational numbers. Whenever you see the word rational in math, it means your discussion is going to be about fractions. because it is the fractions that make the rational numbers different from the integers. So when we were talking about integers and we said -5 is an integer, but -2.5 is not, -2.5 is a rational number. It's a fraction. I'll tell you what's not a rational number. Pi is not. Neither is the square root of 2, or the square root of 8, or the fourth root of 18. None of those are rational because they cannot be written as a fraction. So there's lots and lots and lots of numbers out there that still don't fit in the rational number set. When we include all of those weirdos, those irrational things like pi and root 2, now we have gotten the next biggest set of numbers called the real numbers. And as you can see the way this thing is built, the real numbers is made up of all the rational numbers, which is, by the way, whole numbers and fractions. A whole number is a fraction because you can put it over 1. 4 is a rational number because it can be written 4 over 1, like a fraction. The real numbers includes all of those guys and then all the irrationals as well, like pi and root 2. But believe it or not, there is one more bigger set than that. That's what we're going to discuss today. As you can see, the title of this thing is complex numbers. And the top box is complex numbers. And the complex numbers include all of the real numbers you've ever encountered in your whole life, including irrationals. And it also includes another set, which you see there, called imaginary numbers.
Is Abby Bagley here?
I don't know. Did you send it in as a...
I think so.
Okay. It's all right. It's all right. As long as they know. And I need you to be aware that there are many, many, many words in math that don't have the same meaning in math as they do in common language. Rational is one of them. If you're being rational in regular common language, it means you're being fairly normal. And you can think pretty well and reason through things. That's being rational. Someone who's being irrational is someone who believes something with no good evidence as to why they believe it. But in math, rational means a fraction. And irrational means things that can't be written as a fraction. Totally different. That's the same with the word imaginary. It is really, really unfortunate that when they decided to name this set of numbers, they called it imaginary. Because it makes people like you who are first introduced to it think, well, if they're imaginary, they don't exist. Why should we study them? They exist, and they are going to be part of your life. So you better get used to it. Imaginary doesn't mean non-existent. It means a reflection of real. If somebody asks you, what's the opposite of real? You might say imaginary. That's what occurred to the mathematicians when they had to name this. Because the imaginary numbers that we're going to discuss today are reflections of the real number, just like your hands are. This hand exists. It may be called an imaginary hand, but it exists. So get over yourselves and think, I don't want to discuss this. They're imaginary. I don't have to talk about this. Yes, you do. Because imaginary doesn't mean non-existent. Not here. And imaginary numbers were born out of this idea that if you had to find the square root of -9, for example, it used to be that you would say there is no solution. And what we mean is no real solution. There is a solution, but it's not real. It's imaginary. And here's how we do that. It came from square rooting negative numbers is where this all came out. And so we're going to go with the simplest negative number to square root for a definition. So the definition, this is a definition, which means nobody figured it out. The mathematicians just agreed this would be the definition. Definition of imaginary. And by the way, the symbol we use for imaginary numbers is cursive lowercase I. So we will define the square root of -1 to be I. It's not a real number. It's an imaginary number, but it exists. If you take this definition, which is an equation, and you square both sides, you get this. -1 equals I squared. If you square this side and you square this side, the squaring undoes that square root, leaves you with -1, and it's I squared. So now, for the first time ever in your lives, you can square something, and the result can be negative. Weird. So let me come back to this. This doesn't have a real solution. but it has an imaginary one. So this is how we would do it. Remember I told you that if the square root of a times the square root of b can be written as the square root of a times b inside 1? Remember that? Well, I'm going to split up this 9 right here to be the square root of -1 times the square root of 9. Well, I just told you by definition that the square root of -1 is I. The square root of 9, you know, that's 3. That's an improper way to write it. We put the 3 before the variable, the 3 before the letter. So the square root of -9 is 3i. And you don't have to go through all this. I'm just showing you that it's a reasonable thing to understand. What you're going to do in the future now is just, for example, if I ask you to square root -25, you're going to say that's 5i. You're going to square root the negative, that gives you the I. You're going to square root the 25, that gives you a 5. There will be some other things that I ask you to do, like this, perhaps, the square root of -72. That is not a perfect square. And so we square root the negative as an I, just like we did before. The negative, square, that's -1, square root is I. And 72 we handle like we've always done if it's not a perfect square by finding the pairs we can get to come out. That's 9 times 8. 9 is 3 times 3. 8 is 2 times 4, and 4 is 2 times 2. So I have 3, 3, 2, 2, 2. 3's pair up, that's a 9. 2 of the 2's pair up, that's a 4. 3 comes out, 2 comes out, multiplies together. That 2 didn't pair up. He's got to stay inside. So we handle the number just like we always have. It's just that the square root of that negative now is going to come outside the radical as an I by definition. You're going, well, that's easy and kind of dumb. Well, you're going to see in a minute that it gets kind of fun. A lot of people, when they're first introduced to this, go, it feels uncomfortable to them because it's new and it's strange and it's weird. But as you work with it, it gets kind of fun. It gets kind of interesting because it's not unattainable for you, but it is a little bit challenging. It's kind of fun. So, a couple of notes on things here, real quick, that you need to be aware of. Just as a matter of agreement, I need you to understand 2 things. First of all, if you square root -72 and you write it down like this, say you said, okay, I'm going to deal with that 72. I know that that's a 6. That's what we found over there. That's 6 root 2 I, because you're used to putting I on the back of things. This right here, the writing, the handwriting with your hands, not typing or anything like that, or reading in your book, which is typeset. When you write it with your hands, this could be determined, could be deemed what we call ambiguous, because it could have 2 meanings. When you write it, it could be that your square root in the writing, maybe it went like that, and you're going, well, is that I inside or is it out? Could be the one, which means this is an ambiguous statement. There's 2 ways to deal with it. Either put the I in between, like I did over there. That's how you'll see me do it most often, because this is how I was taught to do it when I was sitting where you are at your age. This is the only option they gave us. But I discovered later that when I had a German exchange student, that you can also write this like this. 6 root 2, put a hook on it, on the end of it. Put the 2 in there and the I on the other so that this hook separates the 2. Then the ambiguity's gone. I is on the outside. So you may put the I on the back if you want when you're handwriting. But you got to put a hook here. If you write it like this, it may cost you something because I can't tell what you mean. Put it like this. This is very clear. The I is clearly on the outside. This is also clear. The I is clearly on the outside. It's not here. So either adopt this method, always sticking the I on the outside of the radical if there's one left, or putting a hook at the end of your radical to separate things that are in from those that are out. Okay? So that's just a convention. That's just something we will agree on. Here's the other thing I need you to be aware of, and this is really subtle. What does subtle mean? Anybody know?
Not very noticeable.
Yeah, not very noticeable. So when I say this is a subtle difference, it means the difference is very small, but it's very important. If I ask you to find this for me, I'm just putting up some easy numbers. Sorry. You will answer this, and only this, not a plus or minus, because this symbol, which is called a radical symbol, when it's actually on something in the book, when you read it and it says evaluate this, it means, this symbol means in the writing of it, principal square root, which is the positive aspect. You don't put a plus or minus on that. It is only when they use that symbol, you only get the positive one. So that if I ask you to do this one, negative 81, you would answer 9i. Not plus or minus 9i, just 9i. You with me? However, this is the subtle part. If I ask you to solve this equation, x squared equals 36. The instinct should be to square root both sides, right? But notice, when you get to here, there is no symbol. There's no radical hooky thing on it. It's just this. This is asking a different question. Even though you will square root to find the answer, this is asking a different question than this is. This is saying find the principal square root of 36, and it's 6. Find the principal square root of negative 81, 9i. Find me the numbers such that when you square them, give you 36. That's a different question. Even though we will square root to find the answer is plus or minus 6. Because 6 times 6 is 36, and negative 6 times negative 6 is 36. This question is asking you to figure out what values of x could I plug in here, such that when I square it, give me 36, and there are 2 of them. This one's saying, give me the principal square root of 36. You understand the difference? Very subtle. This one doesn't have a square root symbol in it, and this one does. When there's a square root symbol on the problem that you're dealing with, only the principal square root needs to be written. Okay, that's kind of a subtle thing. All right, we have gotten to nearly the bottom of page 104. All this stuff so far. Now we're going to take a look at what complex numbers actually look like. Can you go back to the page before and tell me what 2 sets of numbers make up the complex set? Real numbers and imaginary. And the reason they chose the word complex to use to describe them is because a complex number, a truly complex number, has a real part and an imaginary part, like this. This right here is the real part. This whole thing right here is the imaginary part. Together, the combination of these two is called a complex number. This b right here, not the I, just the b, is also real. But it's being multiplied by an I, which makes the term imaginary. So if I have something like this, 3 minus 7i, the 3 and the 7, or the 3 and the negative 7 are real. But this term, negative 7i, is the imaginary part of this number, which has 2 pieces. This is the real part. This is the imaginary part. This is the imaginary part's coefficient, which is real, negative 7. But this is the imaginary part, the whole thing. It's got an I attached. So with that in mind, let's see if you can help me understand. Let's see if you can understand what we're going to do with this. We have 2x minus 7i. This is a complex number. 2x minus 7i equals 10 plus yi. These are both complex numbers, just so you understand very clearly what I'm talking about. This 2x right here is the real part. This is the imaginary part of that number. Negative 7 is its real coefficient. Are you with me? 10 is the real part of this number. This is the imaginary part of this number. And the real coefficient is y. We good so far? If these 2 complex numbers are going to be equal to each other, balanced, then the real parts have to be equal, and the imaginary coefficients have to be equal. What we're trying to do in this situation is try to figure out what value of x and what value of y will make these the same number. There's really 2 equations here. This real part must equal this real part, or they haven't got a prayer of being equal as complex numbers, right? Also, not the I part, just the number on it that enumerates how many i's we've got. That number, 7, the real coefficient, must equal the real coefficient of this one, of this imaginary part, or it can't be equal. The 2 complex numbers. So we've got to solve a little bit here, x equals 5. So what we're saying is, if x has a value of 5, and y has a value of negative 7, then these 2 complex numbers are equal. Otherwise, they are not. So just to show you, if I were to replace this x with a 5 and do the arithmetic, I would end up with 10. And I put minus 7i equals, and over here I would have 10. And if I multiply the y with a negative 7 right here, I would have minus 7i. See how they're equal?
Yeah.
Part for part. And so these are the values of x and y that make this complex number equal to this one. You'll have to do a few of those, but you got to understand, this has to be equal, and this coefficient has to be equal. And you create a couple of equations and solve for it to make them. You following? All right. Now what we're going to do is spend the rest of the time, well, almost the rest of the time, learning how to add and subtract and multiply complex numbers together. A bit of vocabulary. You guys are going to hate this. It's the book's fault, but because we're reading the book and doing big ideas math, you're going to have to speak their language. Before we leave this and start doing the arithmetic, well, I want you to look at the bottom right of page 104.
Thank you.
Okay. You can watch this video on my YouTube channel if you need to. I think the assignment is already in Big Ideas Math, so you can get the assignment there.
Yeah.
Okay, so in the bottom right of page 104, are you looking? See that colored little box there?
Yeah.
This is the vocabulary you're going to have to get used to. When you're talking about a complex number, a plus bi, if b is 0, then the result is a strictly real number, like this. If the complex number I'm talking about is 4 plus 0i, that's just 4. Nobody writes 4 like that. But if this coefficient is 0, you have no imaginary part, and so you have only the real part left, so you have a real number. Do you agree? Strictly a real, pure real number. If you have a complex number written like this, 0 plus 8i, you have a purely imaginary number, because adding 0 does nothing. You have this. That's purely imaginary. There's no real part to it. You with me? The book calls this a pure imaginary. They call this just real. They don't call it a pure real. But the thing that kills me, that makes me so angry about this book is they call this not a pure imaginary, but an imaginary. And it should be called a complex. I have never seen another book do this, but you need to understand what they're talking about. They will call this whole thing an imaginary number, but they will call this one a pure imaginary. See the difference? Still, they call that, even though it should be, it drives me crazy, but that's how they're going to talk about things, so I need you to be aware of that. All right, now we're going to talk about adding and subtracting and multiplying. We're not going to divide these things today. We'll do it by the end of the chapter, but we're not dividing today. So I want you to consider two complex numbers. We're going to add them together. And in the book, it will probably be written something like this. 3 minus 2i plus, I don't know, negative 8 plus 5i. We have something like that. Okay, now I want you to listen to this discussion. It's not hard, but you need to listen. It will look like this in your book. But I need you to know in this problem, there is absolutely no mathematical reason for the parentheses. The parentheses are there to get you to think, okay, I've got a complex, so they're grouping it. I've got a complex number plus another complex number. But mathematically speaking, there is no need for these parentheses. This is the problem you're doing. And the result is negative 5 plus 3i, period. It's just an exercise in combining like terms. You combine your reals, you combine your imaginaries, and write a new complex number called negative 5 plus 3i. That's the result of adding these two. But they're likely to put parentheses around there to get you to understand you're adding two complex numbers, but there's no math reason for the parentheses, okay? So you just collect like terms. Collect your reals, collect your imaginaries, move on. There is, however, if they want to have you subtract two complex numbers, they'll do this. It'll look like that. There is no reason for this set of parentheses because there's nothing out here to distribute. But there's definitely a reason for this set because this has to be distributed. You know what I mean? So really, a situation like this where they're saying you're going to subtract two complex numbers, they put this in parentheses to remind you there's a complex minus a complex. But there's no need for these. But there is for that one because you've got to distribute that negative. So you need to write down on your papers 3 minus 2i plus 8 minus 5i. That shows the distribution that went through both of those. It has to hit both of them. And when that happens and you've distributed the negative, changing the signs inside, then you can collect like terms. That one's 11 minus 7i. So when you're adding, there's no need for any set of parentheses. When you're subtracting, the back set is definitely needed until you get the distribution done. Do you understand? Okay, so there's adding and subtracting. It's not a big deal. Adding and subtracting is just adding real part to real part and imaginary to imaginary and combining them together. Just make sure that in a subtraction you distribute the negative before you do that. Multiplying. That would be more fun. Multiplying is much more fun with imaginary numbers. And I do mean fun. I'm not trying to be facetious. After you've done 1 or 2 of these, you're going to go, oh, that's kind of cool. Makes me, I got to think a little more, but I can handle this. Let me show you. If I ask you to multiply, for example, this pure imaginary times this complex, or this imaginary, like that, that means you got to take this pure imaginary and distribute it through there, multiplying this times this, and then multiplying this times this, remembering the rule, which is I squared equals -1. Watch how this works. I'm going to show you what the result of this is, and I want you to think about it before you say, what? What you think? The result of this is -16i minus 28. You see it?
Yeah.
Some of the rest of you coming to realize that's what it is? You see, squaring I propels you from the imaginary world back into the real world with an extra negative sign. So 4i times 7i is really 4 times 7, which is 28, positive 28. And then I times I, which is -1. So what you really have is positive 28 times -1, and there's no i's left. They got burned up in the squaring, but they got an extra negative with it. You see? So this is actually a -28, and you should put the real part first when you write the answer. So we switch gears with them. Do y'all understand why we got a -28 and there's no I on this last number? Do you understand why that is? The I times the I turned into a real -1. So we got an extra -4 and there's no i's left. Clear? We good? All right. Then let's try multiplying 2 imaginaries. Not pure imaginaries like this one was, but 2 imaginaries like this. -2 plus 5i times 6 plus 8i. Okay. So now we've got an imaginary times an imaginary, or what I would call a true complex times a complex. And those are binomials. They each have 2 terms in there, a real and an imaginary part. So it's not a pure one like that. It's a complex number or an imaginary number. And so because it's a binomial times a binomial, we follow that scheme for multiplying 2 binomials. It's called foiling, remember? So here we go. We get this times this. That's 2 reals. They are still just exactly what you always thought they were, which is -12. Then I take the outside, -2 times 8i. There's only one I involved here, so there's no chance of getting that. The I just tags along, so it's going to be -16i. This is going to be 30i. And this is going to be -40. You all see it? Now, what happens then in multiplying these together is I get the imaginary junk is inside and the real stuff's on the outside. Both of these are now real. This just got an extra sign to it. So I got to add -40 and -12 on the front because the real part belongs on the front. That's -52. And then I combine these guys, which is 14i. That's the result of multiplying these 2 complexes. It's another complex. But you end up with a real part on the front because you multiplied 2 reals. And you end up with a real part on the back because you ended up multiplying 2 pure imaginaries, which gives you a real because the I times I was -1. The imaginary stuff's in the middle. These 2 guys combined out here. Did you follow that? Did I lose anyone? Okay. Now, there's a couple more things I want to show you, and then I'm going to come back to example 4. If you have to solve an equation, now this is different from what we've been doing. We're not doing arithmetic on complex numbers. We're actually solving an equation that will cause us to square root a negative, such as this. This is a different, don't switch gears here with me. I'm going to solve this equation, 4x squared plus 20 equals 0. Well, actually, it says, this is your function. There's your function. Find the zeros. And that means to let your y values be 0. Now think back on what you know about quadratics. This is a quadratic that's going to open upward and be kind of skinny. Do you recognize that? It's also going to be moved up 20 and open upward from there, which means it'll never hit the x-axis. Right?
Right.
And yesterday we said that has no solution. It has no real solution, but today it will have an imaginary solution. It never hits the x-axis, but that just means that its solution will be an imaginary number instead. So we go through the process. Oh, remember also that if there's no x term, then the method of extracting square roots is best. That's what I'm going to do. I kick the 20 over here. Then I divide by 4. And remember what this is asking. It's saying, what number can I multiply by itself to give me negative 5? And the answer now is, when we square root both sides, is the square root of that is I. The square root of that is a prime number, so it's going to be root 5. It doesn't get to come out. And because we are solving, you must have a plus or minus on it. In the process of solving, positive and negative results will give us, when you square it, will give you negative 5. So in the square rooting, in the process of solving, don't forget your plus or minus. Everybody okay on that? We knew this would have imaginary solutions because it never hits the x-axis. It doesn't take very long to imagine what that thing looks like. But now we've got imaginary solutions to those. You have to be able to handle that too. 2 of them. Just like you got 2 when it did cross the x-axis. There will be 2 of them. Okay, now, last thing I want you to learn is, well, imaginary numbers are not just an oddity and a fun little academic game. They use them in many different industries. 2 in particular that I am certain of, and I've seen it, is in the design and maintenance of radar systems. Like when you're trying to find out where a particular ship is out on the ocean with your submarine radar, or if you're in the control tower of an airport and you want to know when your flights are coming in and how close they are to the airport so you can steer them to the right runway, tell the guys where to land so they don't crash. Those kinds of things. You guys have all seen that on shows before, like in submarines or in a tower, and they've got the circular green screen, and there's a hand that goes around it about once every second. It goes beep, beep. Remember seeing that? And it kind of lights up the screen as it goes around, and you're able to see on the screen the location of things with respect to you being in the center. Where you got to look to go, or where you got to shoot your torpedo, or where this plane's coming in so that you can get it to the right runway, whatever. These little blips are on there, and they keep moving closer to the center, which is where your radar is. Well, what happens is a signal is sent out through the air if you're in an airport. Sent out through an air, and it bounces off the airplane. And it just keeps firing out like that. So it just keeps firing out and bounces back and sends information about what's happening to this airplane. Well, what's sitting on the screen is a reflection of what's going on in reality. And I mean literally. What's going on out there in the sky is real. What's going on your screen is a reflection of it. And to calculate and design those systems, to calculate with them and make them work and program things with them, you have to be able to speak the language of imaginary numbers to do the calculating. So it's a very real thing. The other thing that you have to have imaginary numbers to calculate with, which is routine, is anything having to do with this alternating current coming out of the wall. Anytime, and all walls that you plug anything into, anytime you plug something in, you're talking about alternating current. Alternating current, like this is a 60. This is a 60, I can't remember what they call it. But anyway, it toggles back and forth. The signal toggles back and forth 60 times a second. Meaning those poor little electrons in the wire, this is very simplistic, but the electrons in the wire say, okay, let's go this way. And then they say, no, let's go this way. And then they say, let's go this way. And then, well, let's go this way. And they do that all over the place. Every time they reverse, you might think that would be positive and negative numbers. It isn't. It's real and imaginary. And when you stick something in a circuit, like a refrigerator or a blow dryer or a toaster. You plug something in there, that thing that you plug in is called a resistor. And the electrons or the electricity doesn't flow through it quite as easy. As it goes through, it creates heat. That's why your lights light up, and why your toaster heats up, and why your blow dryer heats up. And believe it or not, while your refrigerator cools down. So you'll learn that in physics if you get to it. But those are called resistors. But there are other things inside a circuit, like an inductor or a capacitor. You don't have to know what those are. You just have to know how to deal with them. So please look at example 4. This is how you have to deal with this kind of problem. Look at that funny little table right there and those funny little symbols, and I'm going to read to you for a second here. Top of page 106. Electrical circuit components such as resistors, inductors, and capacitors all oppose the flow of current. They impede it. It's hard for the current to get through them when they're hooked into a system, into a circuit. The opposition is called resistance for resistors, reactance for inductors, and capacitors. So we've got resistance and reactance. Each of these quantities is measured in ohms. The symbol used for ohms is an upside-down horseshoe, and it is the uppercase Greek letter omega. It's the very last letter in their alphabet. It's capital Z.
Whitney Wells, could you come to the office, please? Whitney Wells, come to the office.
If nothing I've said so far makes any sense, it's okay. It's the table that you have to make sense of. When you put a resistor in a circuit, however much resistance it has measured in ohms is treated exactly like it is. Look, resistances are, impedances are. For resistors, they're exactly the same thing. For an inductor, which looks like, by the way, the resistors look like a zigzag, the inductors look like a little spring when you put it in a circuit. Inductors, if their resistance is L ohms, then we treat it as Li. And a capacitor, which looks like two fists coming together to me, it's a little tiny gap. For a capacitor, if its resistance is C resistance, then we express it as negative Ci. So, in the circuit to the right there, the alternating current source, you can see that. That's the one symbol we didn't have, we're not going to account for that. How much resistance do we have to figure out total resistance in the circuit? How much resistance is there in the resistor? 5. And that's treated just like this. Resistance is what it says. To that, we have to add the resistance in the inductor. How much resistance is in the inductor? Look again, find the inductor. 3. And since it's inductance, it's 3I. So we add that resistance. Or that inductance. No, it's that reactance. Now for the capacitor, what's the number associated with the capacitor? What are you going to write? Negative 4I. What's the total resistance in this circuit? 5 minus I. That number is the total resistance, basically. The total resistance or reactance in the entire circuit. It's a complex number. People do this routinely every day when they build circuits and they try to evaluate problems and things like that to figure it out. So it's a real thing. You will want to refer back to example 4 and those symbols for 2 or 3 problems that you can see, like number 33 and 35. 33 to 36 in your exercises deals with that. You'll have to go back to example 4 to remember how to represent them. But you add up the 3 things, putting the correct form of them, and then add them together to get your total reactance. Can you do it? It's not that hard. It's kind of fun. Okay, that's it. For those of you doing this on paper, either because you want to or you're being compelled to, this is a long assignment. The assignment is number 2. And 3 to 73 odd.
3 to 73?
Yes, it's 37 questions, and I'm not trying to make busy work for you. This is brand new, spanking new stuff, and you need a lot of practice to get good at it. Happily, you're going to be doing a lot of what you're going to be doing right at the beginning is, I don't have it up here, is like this. I mean, or maybe square rooting -9. That's 3I. That shouldn't take you very long to do the ones at the beginning, so it's not going to be that arduous, but there are a lot of problems to do. Anyway, lab is open till 7 tonight if you wish. I know there's a lot of things going on, but if you want to come in and study, you can. I'll be here. So, okay, whoever's watching, hope you enjoyed that. See you later. Bye.